Welcome to the Tangent Gentlemen. Each week we start with a topic from the previous episode, then we see where the conversation takes us. Along the way, a question, idea, or disagreement sparks a tangent, and that tangent becomes next week's discussion. And tonight we have our friend and aerospace engineer Connor Johnstone with us, and the topic is space junk, and we're just going to jump right in. Connor, let me start by... You mind if I ask you to maybe explain to our listeners what we're talking about with space junk and maybe how big of a problem or how big of a non-issue is space junk?
Yeah, sure. I mean, first, maybe I should talk about who I am, I guess, a little bit. I don't work for SpaceX, as was mentioned on the last episode, but pretty close. I work for a different private satellite company. But I mean, maybe more importantly than that, and we'll get to it, we do space weather models specifically to help satellite operators avoid collisions in space, which is kind of the name of the game when it comes to the space junk question. So yeah, you want me to just jump in with discussion on it?
You said weather models?
Yes, space weather, which I realize is kind of a weird term. We have weather here on Earth in the lower atmosphere. Lower atmosphere to me being, anywhere planes can fly, basically. Yeah. But in the upper atmosphere, there is atmosphere. It's a lot thinner, but the stuff that it's made out of is different. And in particular, most relevantly, there's a lot of ionized gas up there. Ionized just meaning that the sun's rays have essentially hit it and knocked off one of its electrons, and now those particles up there are charged. And that's relevant when you want to talk to a satellite. So we want to talk to our satellites. We've got to send up, communication signals. We've got to send up radio signals. And those charged particles can get in the way and cause problems. So what we do is we model what we call space weather, which is really just the effect of the sun and the Earth's geomagnetic field on, those charged particles.
So are those satellites, just cursory understanding, there's like lower orbit, middle orbit, and higher orbit. So where are those that are in the ionized parts at?
So, every communication to a satellite has to start on Earth and reach the satellites. So everything is going to pass through the atmosphere, and it's going to be relevant to any satellite in any orbital regime. But you're right. There are really three broad categories of satellites. The first is LEO, low Earth orbit. And that's most satellites, I would say. I mean, the vast majority of when we're talking about space junk and that sort of thing is we're concerned with LEO, just because it's cheapest to get a satellite up there. It's easy to bring them back down. They come back down eventually. And we can talk about LEO versus MEO versus GEO if you want. But low Earth orbit, middle Earth orbit, which is not nearly as used, but it is where GPS satellites are. Among other things, for complicated orbital reasons. And then GEO, or geostationary Earth orbit, which is actually way high up in the sky. I think I'm going to make a fool of myself, but I think it's 32,000 kilometers up. But what's special about GEO is that if you've got a satellite in orbit, particularly if it's in orbit in the equatorial plane, so above the equator, and it's in the geo altitude range, it'll stay over the same, like its orbit takes one full day to complete. So it'll stay over the same point on the Earth. So satellite TV satellites and a lot of government, imaging satellites and that sort of thing that really need to stay over a single spot, those will be up in geo.
So where are the ionization that you're dealing with? Is that to all levels, or is
it has an effect on communication with all levels of satellites, right? Because your radio signal starts out on Earth, and it has to pass through the atmosphere to reach any of these orbit regimes.
Right.
And LEO, or the lower orbit, is the crowded orbit, correct? Or the most crowded?
Yeah, it's definitely the most crowded. I would say there's also some crowding issues with GEO too, but that's handled a little bit differently.
And can you give like any type of perspective on what we mean by crowded, or what kind of clutter are we talking?
Yeah. So, that's kind of at the heart of it all, I guess, right? Basically there are, I think, around 10,000 known tracked satellites that are on the U.S. Space Force tracking list, which you can access if you're ever feeling interested. You can go look at on spacetrack.org or Celesttrack, which is a privately kept one. You can see where all the satellites are. Plus, there's a bunch that they don't publicly release that are not known. So I think there's, I don't know, I'd have to go look it up, but between 10 and 20,000 satellites, essentially, let's say. And the vast majority of those are going to be in LEO.
Yeah, I did look up today. I don't know how many satellites, but I did find something. I forgot the organization, but they track around a little bit over 30,000 objects that are over 10 centimeters.
Right, including space debris. Yeah, because what happens is, you've got, and we'll probably talk about the Kessler syndrome if we're talking about space junk, but this idea that when two satellites crash, or even actually just recently there was a Starlink satellite that it didn't crash into anything, but it had either a battery or a thruster kind of explode and launch a few bits of debris out. And those bits of debris are far harder to track than a satellite. So really, it's those sorts of things that are the problem. Satellites, especially satellites that you don't have control over, are a problem too, but little bits of debris up in space can cause massive damage if they hit a satellite.
Yeah, I was surprised to read about Kessler. What is it, Kessler syndrome?
Kessler syndrome, yeah.
Yeah, that's, I was surprised a guy knew so much about space junk and how to make a terrible bourbon. That was a bad joke, wasn't it? So what is Kessler syndrome?
So Kessler syndrome is this it's a problem that's kind of looming over everyone's head. The idea that as you put more and more satellites up in, well, let's just say low Earth orbit, they're crossing each other at extremely high speeds, like many miles a second, right? Relative to each other, let's 10 miles per second, roughly, which means that any crash you have between those two satellites is going to create a lot of debris, and that debris is going to be spewing off very quickly in random directions because you can't really model what happens when two things crash. So what you're going to have is bits of debris that are going to hit other satellites that are going to cause other crashes, and you get this chain reaction. That's what we're worried about. If we reach a certain density of spacecrafts, we'll get this chain reaction that essentially it's impossible to put anything up because there's just so much debris flying around.
And I think because I never really thought about this, but I read that everything in orbit travels about a little bit over 17,000 miles per hour.
Yeah, I don't off the top of my head know it in miles per hour. I usually think in kilometers per second, but 7 kilometers per second. That sounds about right.
So then when I read that, it just made me think, I wonder how much how much the shrapnel from a hand grenade, how quickly that travels.
I think that's under 1,000.
About a tenth of that. Yeah, like 13 or 14.
So
100 miles per hour.
As it pertains to the Kessler effect, this syndrome, the question I have is, does gravity take a role, and especially in the low Earth orbit? Because isn't the case that stuff typically comes back down and burns up in the atmosphere? So is that ideally what would happen to the shrapnel and the fragments, or it's just what does it hit along the way is the issue?
And that is kind of the nice thing about if were there to be some sort of Kessler syndrome event in low Earth orbit, is that it's not actually gravity, it's the drag force of the atmosphere itself. But that brings low Earth orbit satellites down. There is enough air in LEO that there's essentially air resistance, not a lot, but a tiny bit that brings the satellites down slowly over time. So, even if let's say there was some major thing and every satellite below 600 kilometers altitude, or what's that, 400 miles or something, were to just be, big debris clouds and nothing could fly. if we then wait, depending on the solar cycle and all kinds of things, 5 or 6 years, the vast majority of that stuff will have come down. So that is kind of the nice thing. It's like there's a big reset button basically, but it does require waiting 10, maybe 20 years if it happens up high enough. It's still not good.
Yeah.
So is that what you're trying to, when you talk about communicating with satellites and things, is that to keep an object in the orbit where you want it to be, to counteract the drag you're talking about and the weather and those other things?
Yeah. So that's one of the things that we do at my company, is that we try and keep it a really accurate model of the density of just, the air in the upper atmosphere, because that's the number one factor when you're trying to determine like where a satellite is headed. That's the number one factor, at least in LEO, of uncertainty. So you can say with a pretty good degree of certainty, you can say with 1 day from now, if we just took a measurement and my satellite is here, I know that 1 day from now it'll be roughly, here, within plus or minus, let's say 10 meters to 50 meters. But 5 days from now, that's going to be plus or minus 300 meters, 500 meters. It grows pretty quickly the further you go out. And if you have a better knowledge of the density of the atmosphere at all these points, you can have a better knowledge of where your satellite is. And that can help you if for instance, the Space Force is tracking all these satellites, it can help them determine if two really are like on track to hit each other. And if they are, they can notify the companies that run those satellites and have them maneuver and try and avoid a collision.
Have you been a part of any of that? Have you been involved in a maneuver to avoid a collision?
No, I haven't had to do that. We haven't done a lot of maneuvering on most of our satellite programs. But I essentially have helped the Space Force make that call. Like, when do we tell these other companies when to maneuver? So is it?
I guess I was under the impression that a lot of this, that once they're up and they're kind of, we're leaving them to sort of, basic Newtonian physics to do what they do, but that's really not true. There's actually a fair amount of control once they're up.
Yeah. And we're the FAA, which governs a lot of the licensing and stuff for this, is moving to requiring thrusters more and more on more satellites. So there's a big range. Usually your larger, high dollar, multi-million or billion-dollar satellites made by big companies will almost always have some kind of thruster control or something. But more and more, we're starting to see requirements that even these small CubeSats, which might just be 10 centimeters by 10 centimeters by 10 centimeters at the smallest, they're also being required to have thrusters just to avoid these problems. But it's not true that they always do. Some have no control.
Right.
So there are some regulations then. It's not.
There's a lot of regulations.
Yeah. So what are like what are some of the big regulatory items that you have to adhere to as an engineer? If you're thinking about sending something up into orbit.
Yeah. When it comes to this problem, so control is going to be one of the big things. And essentially all the standard things that you think of when you think of aerospace engineering and building a satellite, like you need all of your systems to be redundant or even triply redundant in most cases. So if one subsystem fails, you can't let that mean, we can't control the thrusters anymore. We have to be able to say, our automatic thruster system failed, but we can still send up manual thruster controls. But our radio subsystem failed, but we can send up to our backup radio or something. There has to be multiple levels of redundancy there. And that's true for all subsystems on a satellite, but it's especially true for things like thrusters. There's also reentry concerns. There's regulations around reentry. Thrusters sometimes utilize like really exotic materials that have really high melting points. So for instance, we had some issues with having some molybdenum on one of our thrusters on a satellite, and NASA comes back to us and says, we think that if you re-enter with this set of molybdenum but it's not going to burn up in orbit. And if your satellite doesn't burn up, in reentry, if your satellite doesn't burn up in reentry, that represents a potential, human casualty risk, right? Like you don't want your satellite to come out of the sky and land on somebody's head, or even anywhere near. So yeah, that's just a little sampling of the regulations, but there's a lot of regulations when you put a satellite up.
So you mentioned the reentry, and when I started into this, trying to get a little handle on this, I was trying to do this comparative analysis between plastic in the ocean and space junk in the sky. Uh-huh. And I really thought it was going to be, it's so much worse. The satellite problem is so much worse. But what I found is, and you just alluded to this, it's really not, because the satellite design is, and please correct me if this is wrong, but it's designed to burn up in the atmosphere. Like, the problem is really not that much of a problem, because particularly most of the low Earth stuff, which is most of the satellites, are designed to basically burn up.
In LEO, that is true. Yeah. So I guess there's a couple of things to touch on there. In LEO, that is true. If you wait long enough, satellites will come down and burn up in the atmosphere.
But not all of it.
Yeah, well, not necessarily all of it. And you might have to wait a long time.
This is Brad, the conspiracy theorist. I saw this when we talked about space exploration a couple weeks ago. Not all of them.
There has been space junk hit the ground, right?
Yeah, it happens. We try and avoid it as much as we can. But, I mean, if you look at the Columbia disaster, that's some space junk hit the ground in that situation, as morbid as that is. But yes, in LEO, the majority of satellites will burn up before they hit the ground. However, there's, I guess from the American standpoint, there's sort of a national security concern there. If there's some sort of Kessler syndrome situation and we can't put up any new LEO satellites for the next 5 to 10 years until it all comes down, that could cause national security concerns, which, I mean, obviously, plastic in the ocean is a very serious concern too, but maybe just different concerns. But then there's also the question of space junk and GEO. And those GEO satellites will take, tens of thousands of years to ever come down because they're so high up. So if there's ever some sort of big, chain collision in GEO, that would be a really big problem.
Yeah. Yeah, that was one of the things I was reading about, is some of the very first satellites they're in GEO and they're still there. Right? They're just
And they're mostly defunct. So I've also worked briefly on a project for a different company that was ultimately, not canceled, but they stopped working on it. And I think NASA's having another company do it now. But the mission we were working towards there is to take a new satellite, fly it up to GEO, rendezvous with one of these defunct early satellites, and I think they were going to refuel it. But there's a whole bunch of methods there. You can either refuel the satellite and get it up and running, or just there's even some plans to kind of capture them, hook onto them and then just move them out to a different orbit where they're not going to be as big of a problem. But there's this concept that was pretty in vogue at least a few years ago, and it's still a little bit interesting and still a little bit people are working on it. But this idea of cleaning up GEO, especially. Because it's never going to, the satellite's never going to come down. If there's any defunct satellites up there, we need to send something up to go clean them up.
So, Scott, you're thinking about the ocean. I was thinking about comparing it to oil or mining. And I thought about it from the capitalist perspective of everybody wanting to be the first to get the next thing out here, like the constellations or whatever they call SpaceX and all that. I don't really understand exactly, but and when you're talking about regulations, the first thing I was thinking about, who monitors? Okay, you can have regulations, but if you put 2 MMA fighters in a ring with no referee, people might not follow the rules. So who monitors these things?
It's mostly existing regulatory bodies in the U.S. that kind of work for other things. So the FAA does some regulations. That's Federal Aviation Administration, but they do some stuff up there. When it comes to communication and bandwidths and stuff like that, the FCC even, Communications committee, basically the people that do TV and radio, also have a say in that sort of stuff. The Department of Defense and military itself often enforces regulations, especially because they have a hand in so many of these things. And then, I mean, we've even had NASA kind of come in and enforce some regulations too on some missions. So
what about the international stuff? Because like the one thing I was reading is the number of, initially it was, initially it was Russia, and then it was or Soviet Union at the time, and then the U.S. But now in the past 10 years, the number of countries that have launched satellites has just gone up tremendously. So are there international agreements or sort of regulatory bodies, or how does that work?
My understanding of that is that there are international agreements to essentially align the rule sets for all the various regulatory bodies. So here in the US, we've got our own set, but then Europe also has a different set that they all stick to, and we make sure that those match up. And then I think any new country, Israel and India have been working on things lately, and other countries, we just try and keep them aligned with what we're doing. The one, I guess, rogue agent in all this, at least from the perspective of us Americans, is that the Chinese explicitly don't. They don't want to be locked into our regulatory systems. So they establish their own regulatory systems and say, we'll handle our own stuff. I'm not sure to what degree exactly they communicate the positions of their satellites, but I know it's not 100%. And they maintain their own stuff. So there is potential for miscommunications there and that sort of thing, which is always something that we're thinking about.
Yeah, it's a little bit like we were talking last week, Scott, with Mars. It's kind of a relatively new frontier. And, like anytime that happens, there's probably going to be a race to make as much profit as possible in my thinking.
Well, yeah, and we talked about that
before regulation can catch up.
That there are currently international agreements, for whatever they're worth, about no country can mine on the moon. No country can take product from the moon and claim it for their own. But then this discussion was about, but what about private entities? Can individuals do that? Because I think traditionally it was the case that most space exploration was country specific. But as we now know, it's becoming more and more private. So
I think I would even go a step further and say, especially in light of recent U.S. political events, I think we could say who's going to stop the country that decides to just go to the moon and mine helium-3 or whatever they want to mine. There's not actually a lot on the moon, but I'm sure people could come up with something profitable. In terms of regulating that, it's really difficult. I'm not sure we have a great solution.
Yeah. I would agree. Again, in light of recent events, I don't know that we can say, oh, well, there's a gentleman's or a general agreement about we will do X and we won't do Y, because I don't know.
We've been through it a bunch of times before.
Yeah, well,
on Earth.
Yeah, I mean, you talked about that, Brad. Like, where overlay U.S. Manifest Destiny, with the space program and with space exploration, and
and that's
I don't think we're killing people with blankets filled with smallpox, but I don't know that we're.
That's essentially where we were in the 60s. I think it was a little bit of a free for all, a little bit of a what can we accomplish? I think what we did find out though, and this is a little bit disheartening, I guess, but unfortunately, for all the things that I've seen tried, the numbers don't work out very well. It's difficult and very, very expensive to go up to the moon or an asteroid or anywhere in space, mine it for any significant amount of material and bring it back.
That was part of our conversation in the last pod, was about the idea of, oh, we're going to go to Mars and we're going to do this and we're going to do that. I'm like, yeah, well, the problem is the temperature and the engineering to actually exist on Mars is stupidly expensive. And therefore, you've got all this built-in costs, and I'm not so sure what you're going to get out of it. I mean, material-wise,
Yeah, there's a number of startups that are interested in asteroid mining and that sort of thing. But in my opinion, in the current state of affairs, they're all scams effectively. I don't know if there are any really serious private ventures to go try and mine an asteroid yet.
Yeah.
Maybe there will be, but it's difficult.
Yeah. This is something I don't in any way pretend to be an expert on any of this, but I'm currently driving my second EV. And so I'm very cognizant of like the metals and like where are the metals coming from and how are we creating, where are the sources of metals and that. And when people say this kind of stuff, I'm like, I can only imagine what an EV that I don't know that there's any molybdenum or neodymium or whatever heavy metal on these asteroids or on these other planets. But I'm sure it's a lot more expensive to have it from Mars or, some asteroid than it is from somewhere on Earth. So,
yeah, generally it doesn't make a ton of sense to think, we've got this material that we need here on Earth for a specific purpose. Let's find an asteroid that has it and go mine it there. Generally, when people think about asteroid mining, they have an asteroid that we've already picked out that has a lot of, insert X expensive material. It has a lot of gold, or it's like made of diamond or something, And so you can just specifically go to that one. I mean, imagine if you could bring back 500 kilograms of like pure diamond, you'd be a very rich person, or, it doesn't necessarily have to be diamond, but I'm not sure that it would be solving any particular use case. It would just be whatever was the most convenient asteroid to go to and whatever it happened to have on it, and if that was valuable.
But wouldn't you say from an engineering perspective that the proverbial startup cost for that would be astronomical?
No pun intended.
Yeah.
Yeah, absolutely.
I don't know.
Yeah. And I think really more than any kind of regulatory needs, that's where we're at right now, is that just no one can do it. I don't even think any country could really do it. The school that I went to get my master's, University of Colorado Boulder, did a mission, OSIRIS-REx, in partnership with NASA and all kinds of other people, but they were involved in it. That did send up a satellite to rendezvous with an asteroid, take pictures of it, land on its surface, collect some samples, and bring it back. And that's, I think very, very little in terms of bringing anything back. And that was still a huge mission. So I don't think we're really bringing back any significant amounts.
So like
you guys haven't watched Landman, though. You guys watched Landman.
I have, yes. Yeah, I have. Not the second season. Don't spoil it for me yet, but I haven't seen the second season.
They're wildcatting, man. You go out and you drill with a 10% chance to hit something, but you're going to make billions. From
that UC project or other experiences you have, I mean, the chemistry teacher in me wants to know, in the end, it's still the same 120 elements and mostly the first 60 of them, right? I mean, isn't that what you're finding everywhere in the universe? At least that's what I used to tell my students anyway. So
yeah. I mean, everything's made from something on the periodic table of elements for sure.
Exactly.
But just some things are particularly rare.
People in concrete vaults.
Yeah. What's that, Brad?
That's why we need to quit burying people in concrete vaults. We're locking up all those essential minerals and elements.
Trace elements, yeah. All of my molybdenum and neodymium and I don't know whatever else I have in me, dysprosium or some obscure element.
That stuff. Quit locking them up. There's a finite amount.
Yeah. I don't know if we want to get into this on this pod. It's not really related, but I had a fascinating conversation with the funeral director when my father died about the concrete vault. So,
what about it?
Yeah.
Well, I think we have to go on a tangent, right? At some point.
Exactly. I mean, it was just, I took great offense. And I said, my father would take great offense that you're expecting me to spend thousands of dollars to like entomb him in concrete. I mean, I was a chemistry teacher. I know what's going to happen. Let's make it happen sooner rather than later. Why put him in concrete? So
I told Cindy that if I die before her, I want to be wrapped around a root ball of an apple tree. And then when that apple produces its first fruit, she has to eat an apple.
Wow. Nice. Shout out Cindy. I hope she lives long enough for her to eat the fruit that comes from the carbon. So, this is a fascinating thing. When I first got into like training teachers and working with teachers, we would do this thing. We would always use the same clip, and it's a clip where we would go to the clip. I didn't, but I used this clip. They would go to like MIT and Harvard, these prestigious universities, whatever that means, the graduation, and they would hand the students a log, and they would say, where does most of the matter in this log come from? And an amazing percentage, upwards of 80%, would say, oh, from the ground, and it's soil, and da-da-da-da-da. And then you would say, do you understand photosynthesis? Do you understand this equation? And, and these kids would say, oh, yeah, it's, sugar and water makes, carbon dioxide and da-da-da-da. Or carbon dioxide, we make sugar and da-da-da. And you say, well, you do realize that that's contradictory to what you just said, because most of the matter, carbon in this case, in the form of carbohydrates, in the plant, in the log, came from carbon dioxide, not from the soil. And these students were just adamant that that's simply not true. But yet you'd say, but what does a leaf do for a plant? And you'd kind of go down that pathway. And it's fascinating because to your Cindy, eating your apple, it really is a matter of she has to capture, or collectively you and your children have to capture the carbon dioxide from you because that's what's really going to make the tree the tree. I mean, relative.
You drink more seltzer water.
More seltzer water, yeah, exactly. But it's fascinating because so many students. What we were getting at as teachers and trainers of teachers was that students have misconceptions. They come into a science class with misconceptions, and we have to dislodge those misconceptions. We have to challenge those misconceptions. We have to use science to challenge those misconceptions, and we have to dislodge those misconceptions. Because the fact is, most of matter comes from carbon dioxide. Most of matter of a tree comes from carbon dioxide, not from the soil. And kids were like, these kids, it was just great to see because it was like, like I said, these allegedly prestigious universities and these Harvard graduates and MIT graduates and, whatever university. Oh, no, that's not true. Well, then show me the science that supports that that's not true because, there's no soil in photosynthesis. I mean, that's not part of the reaction. The product is carbohydrates, and the carbohydrates are what makes the plant, or structurally the plant. So I don't know. It's just interesting. Yeah, I have a story that I love to tell. After my brother passed, I sat outside one night on my patio, which you've had a beverage or two on my patio, Brad. And I had more than enough beverages that night. And when my family came out and said, it's time for you to come in, I'm like, but I'm out here with Kevin. And that was... because I knew that the carbon dioxide that my brother exhaled on that patio got incorporated into the trees that I was looking at.
Yeah.
And I mean, that's crazy me, but that's...
Don't you wish you could keep that perspective all the time without a bottle of bourbon?
I like to think I have. The bourbon, eased the pain. This was, a few months after he passed, but no, I often wander not that I live on some palatial estate, but, I often wander in my backyard and think it's really cool that part of this is my sister who passed or my brother, that's a thing, So
no concrete vaults, damn it.
Yeah, exactly. No concrete vault.
Out as quickly as possible.
Yeah, exactly. I want to recycle and I want to happen quick.
But I do think there's something interesting to say about, what science can provide for us and has provided for us in terms of like spirituality, right? Like this sense of communion with nature that you see because you understand that a part of us becomes a part of those trees is a really spiritual thing. It's a really cool thing. And I think that exploring that as humans is I don't know.
I agree completely.
Optimistic way to look at what science does for us.
Yeah, I mean, incorporate. I used to say this to my students all the time. Your carbon atoms were Abraham Lincoln's, maybe. They also may have been some peasant from the Middle Ages I mean,
a mixture of all of these things.
Yeah, exactly. Right. And
and furthermore, they came from a star somewhere originally.
Exactly. Yes. They did.
Many light years away.
Yeah. So that
well, guess what, guys? We're already over 30 minutes, man.
That's what we do, Brad. That's what we do.
So I think we should, because here on the Tangent Gentleman, we know that the best conversations don't come from straight lines. They come from curiosity. So I've been making a little list of tangents that I felt like popped up today. And if there's any I missed, you guys let me know. And Connor, we're going to let you pick our discussion topic for next week, knowing that the best conversations don't come from straight lines. That's going to be our tagline at the end of every episode. Next guy. So we talked about Kessler bourbon, plastics in the ocean, capitalism, new frontiers, spirituality and spirituality in science, burial and other funeral ceremonies and funeral rites, elements of life, mining, I can't read my own, mining in space, Landman television series.
You talked about that. We didn't talk about
it. And student misunderstanding. So what do you think, Connor?
Well, I think the
one that sticks out.
The biggest tangent that we had over the course of the thing was the spirituality concept that we were veering towards at the end there. I think there's a lot there to talk about. And it sounds like Scott has a lot of thoughts on it. So that might be a good next episode.
Should we talk about how spirituality and science are compatible? Should that be it, or just say spirituality straight up?
I love spirituality and science. I love that.
And science and how they're compatible.
I would love to get real quick, Connors. I would argue with my students that the strong nuclear force and the weak nuclear force, those are like, put that in the book of Genesis. Explain to me how that fits in, you know?
Yeah.
Oh, I can't wait to hear that next week.
You know, I got a bachelor's degree in physics, and my advisor was a devout Mormon. So, I think there's a whole host of ways people can go and kind of view these scientific discoveries and scientific principles from many different lenses. I think there's a lot of meat there to talk about.
Yeah, I agree. Right. I think it's one of the most. I mean, I was raised and I'm somewhat sort of a practicing Catholic, and how do I reconcile that with what I know about science and matter and the rules of the universe that I know, which we talked about before, Brad. We know what we know, but we also have to accept that we don't know a lot, you know?
Yeah.
So,
yeah.
And I put the weak and strong nuclear force in that category because that's for me is the one that I'm still struggling with. How does that reconcile with, matter? What is matter? How does it, I
mean, the standard model is still only just our best understanding of physics too. So,
right.
Who's to say that's the final end game?
Yeah.
Man, I might not be smart enough to make this episode.
We'll have 2 beverages before. Be amazed. There is a direct correlation between alcohol consumption and intelligent conversation. I think it
to a certain
exactly after the 3rd, however, the conversation.
Bourbon, alcohol is an excellent conversation enhancer to a certain point. Then it destroys it.
I think you told me this once, Brad. You said, I am the best version of me after 1 drink and the worst version of me after 3.
Yeah.
I hate to see after 5.
Well, you're young yet. You've got a better tolerance than the old guys do.
I'm convinced 1 to 2 drinks of alcohol is very healthy all the way around.
Yeah,
I think so.
Not to get on a crazy tangent, but it's kind of interesting. Science is giving us an answer to that recently, and it turns out that that's probably not true. We used to think in terms of longevity that 1, particularly 1 if you're a woman, 2 if you're a man, drinks a day is considered healthy. It improves longevity, but as it turns out, that was kind of just some people doing effectively incomplete science, not good enough science, and there were a lot of confounding factors.
Bias too, I'm sure.
Yeah, well, and the big thing that stands out to me is that they looked at people that don't drink alcohol and said, oh, they're not living quite as long as these people that drink 1 drink a day, but they neglected to tweeze out from their data sets that a lot of those people that never drink alcohol because they're former alcoholics. And that has a big impact on your lifetime.
So how does that inform the both data set and the interpretation that it is?
It seems like right now, any amount of alcohol is essentially detrimental to your longevity, even in moderation. But obviously, a little bit, since it was hard to even tweeze out this fact, a little bit is not a big effect.
Yeah.
But what about quality?
I mean, I find, before I started teaching, I was doing PhD work in medical related fields. And I've always found the application of medical research that I did, which personally was with rabbits, extrapolating, not extrapolating that in a data beyond my parameters perspective, but extrapolating it to a different mammal. That was always one for me that I was like, humans are more complicated than rabbits, or humans are more complicated than mice. Like I have a friend, their daughter is doing a PhD in physiology, and she's exclusively working with mice. And we were having a conversation over the holidays about her model. Her work is in like the GLP-1 drugs, the weight loss drugs.
Fat loss,
yeah. And we were just having really good conversations about the percentage of brown fat in those species versus humans. And can you reasonably extrapolate that to make arguments?
Well, and can you ethically get around that? Is the other side
sure,
of
right,
it,
right. That's a great question about science in general, right? How do you do science ethically if you really want to make it real science? And then I would argue there are a lot of other variables that have to be considered when you talk about, we did this experiment with these 1,000 people, and we're going to then say, therefore, the variable that we introduced had this effect. But did these 1,000 people eat the same diet? Did they did they have the same first 10 years? To your point about former alcoholics.
It's a lot of factors.
Yeah, exactly. So I don't know.
Well, maybe a secondary next episode topic is alcohol and the science of alcohol. That could be a fun one.
I just wrote that down, Connor. Did we just come up with our week the following?
There you go.
Is alcohol.
2 for 1.
Only if we talk about it next week, though. We can't just be making stuff up, It's not.
Yeah.
We're not doing second derivative shows, Brad. It's just the first derivative, just the tangent.
What is the second derivative of a circle? At the edge of a curve. The first derivative is called a tangent.
Right.
The second derivative, I don't know. There's probably a term for it.
I don't know. What would that be? So the second derivative would be the tangent to the tangent, right?
Yeah. Well, and if it's a curve,
well, we got to sign off, guys. All right, it's time for us to say goodbye, Scott.
Okay, fair enough. All right. Well, Connor, thank you for joining us. It was very insightful and very instructive. I appreciate it tremendously.
The best conversations are not a straight line.
Yeah.
Thanks, Connor. We appreciate it. We're going to have you on again sometime in the future.
Yeah.
Hope you had a good time.
Anytime.
All right.
I'm happy to be here. Thanks, guys.
Thank you. See you guys.